Everyone, welcome back to another SLHL chemistry structure video. Today we're doing part 2 of covalent bonding. So let's start with VSEPR theory. Now, VSEPR stands for valence shell electron pair repulsion theory. And what this suggests is that electrons will want to repel each other as much as possible because they're all negatively charged. And this essentially is the best arrangement. So the best arrangement so that electrons have the most space between them. And there are 5 main geometries that we will need to know. So let's start with trigonal planar. So trigonal planar, a good example of this would be boron trifluoride, which we would draw out like this. And a trigonal planar geometry will always have one element in the middle and then 3 all sticking out in this fashion. And the angle between these will always be of about 120 degrees. Next up, we have a linear structure, which is quite self-explanatory. A nice example would be here. Carbon dioxide, in which a 180-degree bond is present here on both sides. Next up, we have a tetrahedral structure. So a tetrahedral structure is a little bit more complicated to draw out because we have to be able to demonstrate that this is in fact a 3D structure. So here this triangle is showing us that this hydrogen, it's as if it were coming out the page. And these 4 lines here tell us that it's as if that hydrogen is going behind the page. So here we have butane as our example of a tetrahedral structure. Another 3D geometry that we will need to know is trigonal pyramidal. Now, a trigonal pyramidal structure is actually considered a electron geometry, and that is because ammonia here has a lone pair at the very top. And if we look at rules of repulsion, or which electrons repel the most, so repulsion, lone pairs will always have the highest repulsion. Next up is a lone pair with a bonded pair, and then finally will be a bonded pair with a bonded pair. These repel each other the least. If we see here, we have this lone pair of electrons at the very top, which will push down on the other hydrogens, creating an angle of circa 107 degrees. Also, to add to our tetrahedral structure, this angle up here will be of about 109.5 degrees. And these are numbers that you will need to know. Finally, we have our bent geometry, in which we have a very good example of water with 2 lone pairs coming out of our oxygen, pushing down our hydrogens and creating a 104.5 degree angle between them. The main difference between molecular geometries and electron geometries is that the molecular geometry only takes into account the bonds between elements. So, for example, this right here, in this example, would be a molecular geometry because we have bonds all over. But for example, ammonia here, this presents a tetrahedral electron geometry, as we have this tetrahedral shape presented, but its molecular geometry, as it is only bonded to these hydrogens over here, it would have a trigonal planar molecular geometry. Next up, we are going to look at polarity and just look into what this is. So, in terms of a bond, for example, let's take hydrogen fluoride. So, let's just kind of do a little diagram here to show the general shape of their outer shells. So hydrogen here, we have it bonded with fluorine, and essentially a bond will share an overall charge, and this is called a dipole moment, and this can be represented by a vector. So this overall charge has to do with the electronegativity of an element. The electronegativity of an element is its ability to attract bonded pairs to itself. The most electronegative element being fluorine. You will have access to a periodic table in which you can see the electronegativities of all the elements, so this will not be something that you have to memorize, but it is a rule that you will probably end up knowing regardless. So within this bond, fluorine is closer to fluorine than hydrogen, so this will have the highest electronegativity. So we will draw a little delta minus because it is partially charged. And on this side of the hydrogen, we'll draw a plus as it is partially positively charged, because we can envision the pair of electrons here being pulled closer to fluorine and further away from hydrogen. And this arrow, which I drew here, can be represented by a vector like this. So it is an arrow with a little dash pointing towards the most electronegative element. In terms of an overall dipole moment, let's take the example of carbon dioxide from earlier. So here our carbon is closer to fluorine, so it will be, it is further, so it will be more positive, whilst the others will be a little bit more negative, as oxygen is closer to fluorine and it's pulling those electrons towards them. As this charge is equally distributed throughout the molecule, if we were to draw a line of symmetry, we can see that we have a nice even split. We say that carbon dioxide has an overall dipole moment of 0. A polar bond will be present if the overall dipole moment is above 0, which means that there is a lack of charge symmetry. And this would look like, for example, water, which, as we saw earlier, looks a little bit like this. And if we were to draw our lines of symmetry, with this molecule, we will see that the charge is not equally distributed and that the bottom of the molecule is far more positively charged relative to the oxygen at the center, making it have a net dipole moment. Thank you so much for watching. That is part 2 of IB Chemistry Covalent Bonding. Hope that could help.